Okay, we got two things to do today. One is do a review on quiz 4 and homework 3. Another one is a course project I've mentioned, which weighs 10% for the overall grade for this class. So before we move forward, just let me know what you want to do for the project. It's here. What do you want to do for the project? I mean, should we do a SAR ADC? Seems like it's a one-year project for the Columbia University for graduate students. And we only have 4 weeks left. Can we just do the simulation? Is that possible? Let's have some fun, right? It's a very practical design. And if you look at the link, Columbia VLSI Design, this is the main calendar of the class, okay? So I already provide the link at the bottom of the page. You can click, you can get in there. So always, whenever you see a design, what's the first thing you want to look at? Every time. Yeah, I've learned this from my controllers, right? What's the first thing you want to look at? Power supply. What's the power supply for this guy? 1 volt. Oh, the C5 and 1 mic. The C5 is a fabricatable technology from ON Semiconductor, has been discontinued by MOSIS. So if we design everything on C5, we have to redesign the circuit. And we don't even know if we can reach that sensitivity by using a 5 volt power supply, because that's a dynamic range for the ADC. I mean, if you have 10 bits, but 5 volts has a range, then the resolution will be lower, right? So I mean, 1 volt has its own advantage. It's a low power consumption, and you may be able to reach higher resolution. And the problem is, it takes about 1 volt to turn on an NMOS. If the power supply is 1 volt, how that works? I have to use a different technology. It's not available for us, because if you want to buy, you want to get a quote from MOSIS or from, there's another company called, I forgot the name. So it's providing affordable fabrication process for the US universities, but it's still $1,000 per 1 square millimeter. So which means every little silicon die you are going to fabricate or going to prototype with a company have to pay $1,000 just for 1 by 1 millimeter on the wafer. And normally, when we send a design to the company, we request 5 samples. So if we can scale down everything on the footprint of 1 square millimeter, then for every design, it's still $5,000 for one design. And I have 20 students in the class. They can do the math. And we're not able to afford it. And you can imagine not too many funding agencies are willing to do this, because it's just not creative, because we are doing someone else has done in the past. And it's already challenging for us. It takes a year for these PhD students to design this chip. So what I'm going to say is, if you go to graduate school doing research, if you want to do IC design, which is fine. If you really want to get funding, you have to link this to a specific application. If you just design the ADC, which is really sounds not sexy, no one want to fund you. If you design some sensors on the top of over glass layer, you leave some opening on the top. So if you can lay out some of the metal strip pads as sensors or electrodes, and design op-amp to connect to this electrodes sensing any signals for biomedical signals or any applications, then you can get funding. So that's a reality. Let's come back to the project. So 1 volt power supply, which requires at least a 350 nanometer technology from TSMC, and which is not accessible for us, and we are not able to fabricate this chip either. So we need a model to complete the design before we get that PDK, which is a precise design kit, right? So we don't have it now. But Dr. Baker's textbook provided a really good model for low power design or small technology design. So what's the difference between short channel and long channel design? So this book provided two models which are not fabricatable, but which is fine, just for you guys to practice. One is one micron. Remember the 1 micron technology? Mm-hmm. What's the threshold voltage for NMOS? What's the threshold voltage for PMOS? So 0.8 volts for NMOS and 0.9 volts for PMOS. And I don't think you can use that one because the 1 volt is not able to drive it thoroughly. And we normally use 5 volts to drive it. And also, this textbook also provided a 50 nanometer design. Probably have seen that in the past. Have you? Which is a 1 volt design, 1 volt power supply. So if you look at the back of the book, right? So there are two tables appended to this textbook. It's long channel, MOSFET, parameters. So provided all these parameters for the model. I don't know where he got it, but we can use this model for LT Spice, definitely. Definitely it's not perfect because it's not fabricatable. It's just the educational model file. On the other side of the page is a 1 volt design, which is 50 nanometer technology. So I think we can design everything by using this model file and simulate it. If that works, I think we can transform everything to another smaller technology, not smaller than this, but similar, like 180 nanometer technology from TSMC, which is $1,000 for each 1 square millimeter. And I'm going to ask, since I'm going to teach this class again in the fall, and I'll ask these students to lay it out if you get a successful schematic. So it's a year-long project, which is reasonable. And it's not reasonable to ask you guys to do both, right? Unless you love it, you want to do it, let me know. But we cannot do it anyway because we don't have that technology. We don't have that PDK. Cannot do it. So let's do the design in LT Spice. And I haven't done it by myself. That's called a project. If I have done that, it's called a lecture. But I did part of it. I'm gonna introduce that to you guys pretty soon in this class. So before we move to that, let's do our review for the quiz and the homework assignment, because I saw a lot of problems in there. So that's why I decided to let you guys do another quiz on Wednesday. If you refresh the browser, you can see. On Wednesday this week, there will be a quiz 5 on stick diagrams again. The reason I want to do that because I feel you guys hate it. That's why I want to do this again. You just need more practice. Repeat and repeat and repeat. You'll eventually get it. It's like swim and like drive a car. Same concept. I have provided I haven't posted this link to the website, but I already posted the link to this solution to the website. We can check it out later. But I'm going to run this anyway in the class. So for the one let's do the homework ones first. We only start with problem E, because all the other ones are super simple. E is G equals to A or B, C or D, and the E. Or logic, PMOS in series, and logic in parallel with these two in series, and in parallel with E. A or B in series, right? So it should be like this. And then C or D and E. For the PMOSes. For NMOSes, or means in parallel. And eventually a single E at the bottom. So here's the AOI logic. So what about the layout? 5 transistors. So we need a 6P plus. One, two, three, four, 5. These two in series, and in parallel. So I can introduce the wire to here because I know these two are in series frozen. Right? So I can split it from this P plus to these directions and merge. So this part is this part. And I still have an E, this PMOS in parallel with everything here. How do I want to sort it out? Look at VDD. VDD has 1, 2, 3, so totally 3 branches. 1, 2, just introduce another one. 3, and merge to the same node over here. So this is the E. And we're done with the PMOSes. Now let's draw the NMOSes. 1, 2, 3, 4, 5 gates. Parallel, series. I have to figure out AB in parallel first. So I introduced a wire to here, so I can get these two in parallel. So these are A and B. And then in series with this point, I need another two, C and D in parallel. So what I can do is, if you have tried this for a few times, you can figure out it's not working. If you do these two in parallel and then this in series, it's not working. Try it by yourself if you like. It's not working for this one string. So the way to do that is you just swap the location of this one and this one. It's not going to change anything because they are in series. No matter where you connect these two, you just plug into the middle. You know what I mean? So you want to replace this part with this circuit. That's A, B, E, C, D. Whenever you find out the layout is not working for this topology, you have to change the schematic accordingly as well if you want to just use the one string because it saves some kind of space. It's not a lot of space, but it's saving space. If you have a lot of bits over here, it's going to save a lot of space. But let's try to use just one string if you can. Okay. Is everyone getting that? I'm swapping the location of this one. This one is not changing the result. Because they're in series. It doesn't matter where it is, right? So the benefit of doing that is I'm able to implement this circuit using just one string. So this signal being introduced to here, I got two, so I got AB in parallel, and then directly in series with this guy, just directly let signal pass this gate, which is E, and then in parallel. That making sense? So which one is which? Let's just label it. So in whatever you are going to turn in, not just in the quiz on Wednesday, and also for any of the solution you are going to provide on the paper, do not draw all the wires. It's just totally a huge mess because I couldn't see which one is being connected where. It just drew all these critical paths for the connections, and then just label the signals. You don't have to connect all the gates, just label it. So for this one, let's take a look at it. So here is VDD being introduced to here, and I got A and PMOS, right? So AB here first, so I just label it AB. Can I do BA? BA, or has to be AB? Because A is on the top, so it has to be AB. Here, CD. Here, E. And then comes down to here. Then AB first. Doesn't matter which one is A, which is B. Doesn't matter, but what's the better option? What's the better choice? BA? Yes. So you can directly draw a straight line, connect the gates together. And then E, no choice, just E. And then CD. Do you have a better option? CD. But you have to drill a hole to metal 1 because it's gonna intersect at some point. If you put a D here, then C has to go to metal 1 and then make a connection to C. So it's better to do CD. So you can directly do this, right? No intersection. I don't think there's a number. Just visually, you don't want that to be too long. Keep in mind, just do the calculation. It's 200. It's 200 ohms per square. If it has to be a little bit longer than usual, then you just make it thicker. Is that working? Yeah, make it thicker so the resistance will be lower, right? Definitely. Yeah. But normally, you do not make all these connections use poly. Just whenever you get a chance, just convert it into metal 1 and make the connections. As for E, F is simple. G, A, B, or C, D, like this. Yeah, so that's a great booster. AB for PMOSes, parallel and series. Parallel or series. Parallel. You have to make it parallel by connecting all the two terminals. Otherwise, they're not in parallel. And then in series with CD, no, NMOS, AB in series, CD in series, AB in parallel, and then CD in parallel. If I introduce a VDD here, so AB are in parallel, and I need the other two in parallel as well. Right, just make a connection. AB in series, CD in series, super simple. So let's label the signals. Doesn't matter which is A, which is B. Doesn't matter. So A, B. But eventually find out it matters. Because these two are in series, and A, B is like this. So this must be A, this must be B. So you want this one to be B, this one to be A. So you can directly draw a straight gate to make the connection. And now here, these two are in parallel, so these two transistors are C and D. And it is CD here, so it's better to have a C and D like this. So you can directly make the connection. That's F. Any questions by far? No, you're good? Okay. G. All these problems, I just randomly created them. I didn't even demonstrate it after I made it. I should be able to do it. Which is fine, but eventually sometimes you will find problems with all these examples. Sometimes I'm going to show it pretty soon, but never mind. The bar has been split, and the sign has been changed. So according to De Morgan's law, you want to convert it back. It's going to be AB or C, this entity, or D and the bar on the top. So you have AB in parallel for the PMOS. In parallel must be in parallel, and then C and D in series. Four. How? Pretty simple. Introduce a wire to here in parallel, and then series output signal. If I draw it here, so these two are in series, grounded, that's A and B. And for the other two, I want these two in parallel. So I just introduce another one here and ground it. So these two are in parallel. Now let's label the signals. Let's look at the order, because these two has to be A and B. So I prefer this to be A, this to be B. And C and D in parallel doesn't matter about the order, but this matters. So this has to be C, that has to be D. So I prefer this to be C, this to be D. So I can directly make the connection. Is that making sense? Any questions anywhere? No? So I think the way, if you are not really good at this by far, I recommend you just after the class, do not look at the solutions, just try to repeat it by yourself. If you didn't see, cannot get the stick diagram done with one string, then you can just refer to the notes. But before that, just try to do it by yourself and repeat every single problem I have covered in the lecture, in the notes, and everywhere in the quiz, in the lecture before, the first time I covered it. Okay, that making sense? That's a way to learn it. Just follow. It's no brainer, just follow, okay? Just follow and repeat, then you're done. I'm pretty sure you can get it. Then last one. So I told you, whenever I just hide my eyes and just create all these problems, I got issues. Some of the problems are stupid, like this one. I mean, but no one asks questions, which is scary. No one asked me about it. You probably already realize it. You don't want to waste time on visiting during office hours and ask questions, or you just didn't see the problem. Uh, but I didn't see a. I saw probably one or two correct answers, but I didn't see a brilliant answer, which I'm a little bit disappointing. If you just draw this, I'm gonna give you some extra credit on that. But I didn't see this. But if you do this, which most of you guys did it, which is fine because you can still design a circuit out of it because, you know, sometimes, I don't know, probably nobody will do that. But imagine if you have two signals feeding into a circuit and you want to always get a VDD out of it, you definitely doesn't need a circuit because you can directly disconnect everything and short that VDD to the output. But the signal can change, right? You do have two signals. So you can still design a circuit which always pull that output to VDD, which is still working. It's just not changing at all. It's just always going whatever A and B's are. It's always pulling everything to VDD. So you can still follow everything like this. Then I can design the AOI logic out of it. AB is unlogic, so A and B should be in parallel. And in parallel with these two guys, in series. Wait, AB in series and in series with like this. If you look at circuit, here's the output. And you can find out, let's try all these options. If A and B's are zeros, or one of A and B is zero, then it's always pulling everything to VDD, right? So whenever A and B are ones, these two PMOSes are open, so it's still pulling VDD to G to VDD. So it's always VDD. So A and B in parallel, and in series. And here's the output. And then A and A not B not in parallel. And then A and B in series, so shorted to the ground. So AB But label A, B here, and these two are in parallel, so they are A naught, B naught. And then A naught, B naught. And in series, AB. You can still get something out of it. Right. Now let's look at the quiz. A, B, C, D, E. First, simplify it. Oops. Five. How to do it? 2 in parallel and then 3 in parallel. Can be challenging. So if you introduce this, you know this structure is 2 p-MOSes in parallel, right? This is what you have learned. And then 3 in parallel. You just remember some of the structures you have used so many times. It's always working. Two in parallel just looks like this. 3 in parallel, you just want to make it in a different way. And how to do that? So connect this. And now let's see if that's the case. That's 3 in parallel. Just memorize it. See if that's working. 2 in parallel, the signal is over here. And then from here, you need 3 transistors in parallel. So this signal, that's the first, and second, and third. Merge to here, and being shorted together, that's one node. So where is the output? Right? 1, 2, 3, 4, 5, 6. This is simple, very simple. Done. So let's label the signals. It will be A, B. CD in parallel, doesn't matter which is which. We can optimize it later. I'm just gonna label it randomly. And then you got AB. So you are finding out that it's better to have a AB here instead of BA, right? This is better design. And CDE, perfect. Questions? No? Great. Second one is relatively easier. AB or CDE or BC. First, simplify it. I'm joking since you cannot simplify it. Just directly do it. AB CDE BC AB CDE BC five. Oh no, God, how many? 7. I skip it. Let's do something. 1, 2, 3, 4, 5, 6, 7, 8. Two in parallel, 3 in parallel, 2 in parallel. So still do this, 2 in parallel. And right after it, since we have done a very similar one, see here, 2, 3. So what we did is like this. So we can use the same method, implement that logic. If we do that, how we did it, we connect here, skip 2 gates, and then see if that works. Here, and then this. Let's see, 2 in parallel, and right after the signal, I got 3 in parallel. 1, 2, 3, and merge to here. And right after it, I got 2 in parallel. How? Output. This is easier, I think. A and B, definitely, grounded. And then 3 in series and 2 in series. So the signal. Okay, let's label the signals. A, B, doesn't matter which is which, C, D, E, B, C. Here, it matters. I can swap these two. And C, D, E, and B, C, right? Any questions or anything? No? Can we move forward to the course project? Yeah. You still remember the voltage doubler we learned partially in circuit 1, partially in analog? I'll show you a circuit like this, so then you can let me know what is that, okay? If I have a circuit like this, so what is this circuit? It's an AC signal. Here's VL. What is this? That's 0. It's grounded. So the voltage being applied to these terminals can be plus, 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 plus. Right? It's like plus minus, right? So that's a voltage drop. It can be, this is higher, this is over, this is above 0, and then it's going to swing up below 0. So this becomes more positive. So this becomes a negative voltage, which is going to block this diode. So this is a half wave regulator. So what's going to happen here is you're going to have a, so this is a filter. So the cap is normally pretty large. So it is able to stabilize or filter out all these high frequency signals. So the output becomes, that's input. Let's draw the input first, okay? And the output. And after the filtration, the filter, it's pretty close to a DC signal. It's called half-wave rectifier. And we are not going to use this one for the project. So we are going to swap the location of the capacitor and the diode. We are going to get something like this. And we're going to use a square wave, swing around there. That's V in. So what is VL and why? Here's grounded. Think about it. So AC signal can pass the capacitor. Why is that? I mean, how? It's a dielectric material in the middle. Is it really passing that capacitor? It's not, right? It's pushing the charges away from the other side of the plate to somewhere else. So something like you have a cap. Whenever you have positive charges on one side, it's going to attract negative charges on the other side. Whenever it's attracting negative charges or electrons to the other side of the plate, what's happening? It's pushing these positive charges to the other side. It's pushing the positive charges away from the plate. Because originally, all the metals are electrically neutral, right? So whenever you get negative charge, the plate it has to lose some of the positive charges to the other direction. So whenever the positive charges are being pushed away, it's forming a current, right? So which means whenever you are pushing, you're dumping current or charges to the one side of the plate. It's pushing positive charges to the other, away from the other plate. So it seems like the current is passing the capacitor, but actually it's not. That making sense? That's how that works. And because the same direction. So the direction of the positive charges is the direction of the current, right? Because this is going to this direction, and the other side has the same direction for the positive charges. But if you have a DC voltage here, 5 volts, what's the voltage here? DC, keep in mind. No, I didn't ground it. Did I ground it? So what's the voltage there? Is that -5? Because I have positive charges over here. So it should be like, looks pretty negative. Is that -5? Yeah, there's nothing here. Unknown, it's just nothing. It's just a floating wire in the air, just nothing. So why the AC signal is able to pass but DC cannot? Yeah. So this only happens when you close the switch. So you get a current. After it's stabilized, there's no current. It's just stabilized over there. Now let's come back to this voltage doubler. Okay. See how that works. Number 7, I guess. Page 7. Let's look at this circuit. What's happening? It's always changing, so it always got current being dumped or being discharged from the cap. It has current flow. And so whenever, for example, okay, let's look at for every single step. So if I have a negative 0.5 volts to be applied to this circuit, what's happening actually? Just for this really short period, I turn on the switch and start oscillating. This is the very first wave being received by the circuit. Very first wave, okay? So that's time 0. I just turn it on. So there's a negative 0.5 volts being applied to here, which means here is 0 volts, here's negative 0.5 volts, right? It's grounded, so it's always 0. So here will be negative 0.5 volts because this is negative 0.5 volts being applied to here. That's plus minus V in. So what's going to happen? It's really short, very short. So here's higher voltage, ideal diode, no VB. So whenever it's forward biased, it's able to conduct current from here to here. Here's higher voltage, here lower voltage. So it's going to charge up the cap to what? Yeah, where's higher, where's lower? Right? And at the second, so this is done, and now it's here, 0.5 volts. What about now? Originally, it was charged up to 0.5 volts from right to left. But whenever you are trying to increase the voltage at this node from 0.5 to 0.5, what's happening for the charges originally charged or stored in the cap from the previous phase? It has nowhere to go because it's a reverse biased diode. So the charges will stop there and cannot go to anywhere. So that 0.5 is still there. Why? Because it's not able to discharge it. Why? Because there's a bar here. It's reverse biased diode. And now let me know what's the voltage here compared to the ground. Why? In series, 2 batteries. Is it 2 batteries? the KVL. Two batteries, what's the voltage at these two terminals? If I ground here, I ground here. Here it goes to 1 volt. What's happening actually? Originally, the oscillation is from negative 0.5 to 0.5. And after running the signal into this circuit, you are getting what? Now I have to look at the next cycle again to confirm the conclusion. So the next cycle, it's going to come back. Here. Still have this 0.5 here stored because there's nowhere to discharge it. And now what's the voltage here now for V in? So what's the voltage here? Negative 0.5. Or you can say it is plus minus 0.5 volts. Is that correct? So what is V out? Drop 0.5 volts and then increase by what? 0.5 volts. What's the voltage here? 0 volts. So it keeps going. That's the input signal from negative 0.5 to 0.5. The output will be what? 0 and 1. Just being shifted up by 0.5 volts. And you can run this through a rectifier to filter it, only leave the low frequency stuff to the output. So what you're getting? It's a 1 volt DC. That's why it's called a voltage doubler, because it's doubling the amplitude. Originally that was only 0.5, but now I got 1 volt. That making sense? Okay, so on Wednesday I'm going to cover more about the project where I'm going to use part of this circuit for the charge pump being used in the sand hole circuit. Right? See you on Wednesday. So we have a lab tomorrow, right? Okay.